Hi everyone. In this section, we were going to discuss about the tension test on MS rod. So the main aim of this experiment is to study the behavior of mild steel under tension and to determine the material properties like yield point stress, ultimate stress, percentage elongation, Young's modulus, etc. Okay. Before moving to in depth of experiment, we should understood how the material will behave during a tensile test. This can be easily explained by stress strain curve. Okay, this curve represent the shown curve represent a typical stress strain curve for a ductile material like mild steel. Okay, we can see that when a ductile material like mild steel is subjected to tensile test, then it passes to various stages like A, B, C, D before it become failure. Okay, so actually the stress strain curve is the graphical representation of a material when it is subjected to loading. As we can see that the y-axis in the stress strain curve is usually stress and the corresponding strain developed will be shown in the x-axis. What is stress? Stress is load by area. Strain is the change in length by original length. Okay. So the first region of the strain curve is the proportional limit. Proportional limit is the point on the curve up to which the value of the stress and strain remain proportional. That is, the stress is directly proportional to strain. That is, which obeys Hooke's law. Okay, from the figure we can see that the point A, okay, point A is usually known as the proportional limit point, or it also known as the limit of proportionality. Okay, and the stress corresponding these two region, that is O2A, is usually known as proportional limit stress. Okay, then next region, the region O2B, okay, from starting O2B is usually known as the material will elastic limit region, or the material will behave like elastic. Okay, what will happen in elastic limit for a material is the limit beyond which what will happen, the material will not come back to its original position when the external load is removed. Okay, when the external load is removed. In the stress strain curve from point A to B, okay, point A to B, B is usually known as the yield point. Okay, the B is usually known as the yield point. The material exhibit elastic properties. Okay, so totally O to B, the material will behave like elastically. Then O to A, we can directly say that the stress is directly proportional to strain. Then A to B, even though it behave like elastically, the stress strain relation is not linear. Okay, then the point B is usually known as the upper yield stress point. Okay, the beyond the elastic limit, a ductile material will exhibit plastic properties. Okay, plastic properties. The upper yield point is the point where the maximum external load or stress is required to initiate a plastic reformation inside the material. Okay, the strength of the material corresponding to this point B is usually known as yield strength, and corresponding point is known as yield point or upper yield stress point. Then the point C is known as lower yield point stress. Okay, after this point C, what will happen? After this point C, the material length will increase with a very small increase in the tensile stress. Okay, it will sudden increase in length without a increase in stress. Okay, or we can say that it is the point where the minimum load required to exhibit plastic behavior in the material. Okay, B is the maximum load required and C is the minimum load required to exhibit plastic behavior of the material. Then point D is usually known as the ultimate stress point. What will happen at this point? At this point, the material will reach the maximum strength. That is, the material strength corresponding to this point D on the stress strain curve indicates the ultimate strength of the material. That is, the maximum stress of the material which can withstand before it become breaking. Okay, after this point, what will happen? The necking will occur. Necking means the reduction in cross-sectional area will occur. After that, it will become fail. Okay, so the point is usually known as fracture point or breaking strength point. Okay, the stress associated with this point is known as breaking strength of the material. Okay, this is the typical behavior of a mild steel when it is subjected to tensile forces. So, in order to find out this stress strain curve, we should conduct a tension test on UTM. So, the apparatus required for the tension test are universal testing machine, extensometer, screw gauge, punching tool, scale, etc. Okay, first one is universal testing machine. We are all familiar with universal testing machine as we discussed in double shear test in detail. We know that it is mainly consists of two units, one loading unit and control panel. This one is the loading unit and control panel. In loading unit we have top crosshead, middle crosshead and bottom table. The tension test is done in the upper portion. Usually tension test is done in the upper portion and the compression test is done on the lower portion like double shear test, bending test, etc. Okay, and this portion is the control panel. Here we have dial gauges and the control buttons, right valve and left valve, then weighing, oil tank, oil pump, etc. Okay, so next one is extensometer. Extensometer is actually used to find out the deflection in the member or a specimen when it is subject to tensile test. Okay, we will place the extensometer at the center of the specimen. Suppose this red color showing the specimen, we will place the extensometer on the in between on the specimen, and we will find out the deflection happen when this sorry, and we will find out the deflection of the member when it is subjected to loading using these dial gauges, two dial gauges. Usually the minimum least count of these dial gauges is 0.01 mm. So we can move on detailed procedure. Initially we will find out the diameter of the rod using vernier caliper or screw gauge and find out the cross-sectional area using the equation pi d square by 4. Okay, we will find out the diameter of the specimen. In usually the diameter inner and outer edge of the diameter are a little bit more than the inner diameter in order to grip the specimen firmly on the UTM. Okay, we will find out the middle of the diameters and find out the corresponding cross-sectional area. Then after that we will mark the center point of the rod. We will mark the center point of the rod and punch the center point using a punching tool, and also punch the half the gauge length of the on both side of the center. Gauge length means this is the gauge length. Gauge length means within which the failure will occur, and we can calculate the gauge length using the equation 5.65 into root A, where A is the cross-sectional area of the rod. Okay, after getting this gauge length, we will mark this half of the gauge length on either side of the center point and punch the same. Then we will take a clear length, say 16 centimeter on the rod, and leaving some length on both sides of the rod, which are used to grip or fix the rod or specimen to the UTM. This is observation and calculations for the for finding out the gauge length and diameter of the specimen. Usually we are doing the diameter, finding out the diameter of the specimen using screw gauge, so that we have to find out the zero, correction and least count, and accordingly find out the diameter of the specimen. Now after that we will select the load range of the UTM. Okay, by calculating the maximum expected load on the specimen. As we know, there are mainly three there are mainly three load ranges in the UTM. In order to choose the appropriate one, we will calculate the maximum expected load. For that, we are assuming the ultimate tensile stress between 420 Newton per mm square and to 520 Newton per mm square, depending upon the grade of the steel. Using this value, that is ultimate stress, we can calculate the ultimate expected load as ultimate tensile stress into area of cross section, that is load is equal to stress into area. Okay, after getting this expected load, say suppose we will get some 35 or 90 kilonewton, we can select the load range as 0 to 100 kilonewton. Okay, now we will fix the specimen on UTM and set the load as 0, and also fix the extensometer on the rod, set the readings on the extensometer also to the 0. Okay, in order to fix the specimen, we will fix the specimen in between the upper part and central part of the UTM, this upper part and central part of the UTM. For that, we will open the grip provided. We will open this grip. Here we have some grip. We will open the grip provided on the upper head first and keep one end of the specimen inside it. One end of the specimen inside it. We will lock it. Okay. With the left valve in a fully closed position, and open the right valve and loose it after the lowering the table. We will slightly lifted the middle table. Okay, in order to adjust this length correctly, gauge length correctly, we will using this wheel, we will adjust the table, middle table. Okay, and fix the specimen correctly. Then after fixing the specimen correctly, we will fix the extensometer on the rod, and we will adjust the zeros in the dial gauge corresponding to the two gauges. Actually, we will actually the deflection recorded by the both dial gauges are noted, and the mean value is the actual deflection of the material. Also, we will do the zero correction on the load pointer with the zero adjusting note on UTM. Okay, after that, what will happen? We will close the oil release valve and the loading valve, start the machine. We will start the machine. In order to apply load, with the left valve closed, open the loading valve, that is right control valve, gradually and start loading. Usually the left valve is for unloading and the right valve is used for loading purpose. So we will open the loading valve gradually and started loading. Okay, go on increasing the load and note down the extensometer dial gauge reading for a particular value of load increment. Okay, in this table we can see that we will find out the left and right hand of the dial gauges on the extensometer for a particular interval of load increment, say 2.5 kilonewton, 5 kilonewton. Likewise, for a particular increment of load, we will calculate or we will note down the both ends dial gauges reading, and the mean value is the average extension in mm. Okay. Now, when we will remove this extensometer, we will remove the extensometer as soon as the extension is beyond the proportionality limit. Okay, proportional after it's reaching proportionality, crossing the proportionality limit, we will remove the extensometer. Okay, and how we will identify this proportionality limit or yield point? Usually, as the load is increased beyond the proportionality limit, that is when it become yield point, we can see that the load pointer is this one. Okay, when goes on increasing the load value, when it is reach the proportionality limit or yield point, what will happen? This needle becomes stationary for a while. Okay, this needle becomes stationary for a while. The load corresponding to this stationary point is known as yield load. Okay, for a particular time, what will happen? The load, this load pointer will remain stationary, and that point is the yield point. Okay, then what will happen? Then again we will continue the loading, and at the maximum point of loading, a neck is formed on the specimen. At this point, the pointer goes in the backward direction. The farthest point up to which the needle moves indicate the ultimate load. Okay, I will explain in detail. Once it get yield point, okay, when this needle become stationary for a while, we will note the yield load. Then again we will continue the loading. What will happen? The needle will moves moves on at a particular point, or a particular point. What will happen? The needle or pointer will moves opposite direction. It will moves on opposite direction. That is, at this point what will happen? The load become maximum. That is, the material which can withstand the load become maximum. After that what will happen? The pointer will moves opposite direction. That is, the load become decreased. Okay, for that, at this particular point, when the load become decreased, what will happen? The cross sectional area of the specimen will reduce. That is, the necking will happen. So carefully watch the motion of the pointer in the backward direction and note down the load at which the specimen break. This is the breaking load. Okay, after reversing the load, we should carefully watch the breaking load, that is the material at which the breaking happen. Okay, after breaking the specimen, switch off the machine and release the rod from the grips. Close the loading valve and open the release valve so that the oil pump back to on the oil tank. So this is the ultimate failure that will happen on the material when it reaches the maximum load or ultimate strength. What will happen? The necking will happen. Necking means the reduction of cross sectional area will happen. Then what will happen to the load? The load will decrease. At a particular point, this necking will increase and the specimen will break, and this type of failure is known as cup and cone failure. Okay, these are the values we will note down while doing the experiment. Yield point load, ultimate load point, breaking load. Okay, then after the specimen breaks, we will place the two broken pieces together and measure the distance between the punch mark near the breaking point. Then we will measure the reduced diameter at the neck. Okay, then again we will plot the graph with load along the y-axis and extension along the x-axis. Based on the values from the graph, we will calculate the Young's modulus E of the material. Okay, using the load and extensometer reading, we will plot a graph and find out the Young's modulus of the material. These are the calculation that we have done. Initially we will find out the diameter of the specimen using screw gauge or vernier caliper. From that we will find out the cross sectional area of the specimen using the equation pi d square by 4 by mm square. Then after the specimen will break, we will calculate the neck area, reduced area, which will be denoted as d1, and corresponding area is calculated as a1, that is pi d1 square by 4. Then we can easily find out the reduction in cross sectional area using the equation delta A is equal to original area of cross section minus reduced area of cross section. Then again we will find out initial gauge length, that is the initial length of the specimen, gauge length of the specimen, and final gauge length of the specimen, which is denoted as L dash. This gauge length is measured after the specimen breaks. Okay, from these two values we can find out the extension measured for the above gauge length. We can calculate extension measured for the above gauge length, that is delta L is equal to L dash minus L. Okay, after getting all this value, we can find out the modulus of elasticity using the equation P by delta L into L by A. Okay, P by delta is the P by A is the what? P by A is stress by L by delta by is the change in length by original length. That is stress by strain is equal to modulus of elasticity. Using this equation, we can find out the modulus of elasticity. Okay, then from the graph, from the slope of the load deflection graph, we will directly get P by delta L, right? Okay, while drawing the load versus deflection graph, using the slope we can directly get the P by delta L value. By substituting this, we will find out the modulus elasticity of the material. Now we can calculate yield point stress as the load at yield point divided by original area of cross section. That is, stress is, these all terms are based on the basic equation, stress is equal to load by area. So yield point stress is the load at yield point divided by original cross sectional area. Ultimate stress is what? Ultimate load by original area of cross section. Then nominal breaking stress, breaking load divided by original cross sectional area. Then actual breaking stress, breaking load divided by what? Reduced area of cross section. Then percentage of elongation is increase in length by original length. In terms of percentage, you have to multiply it by 100. Okay, percentage in reduction area can be calculated using the equation decrease in area divided by original area of cross section into 100. Okay, from this calculation we will get the material properties of the specimen using tensile test. If you have any doubt, please free to ask. You have also referred the link provided for the virtual lab. Thank you.